Brian Pailes with Vector Corrosion Services. He'll be talking about non-destructive testing to better define repair quantities.
Today I'm going to talk about non-destructive testing and ways to better identify repair quantities. And really, to start is what are the issues facing owners out here today? Big issue, how do we properly determine repair quantities? We've historically as an industry dealt with sounding and visual inspection, but we all know that those will underestimate our true repair quantity. As we start chipping out some concrete, those patches are going to start to grow. And the impacts to underestimating these repair quantities can be very costly. Obviously we get change orders from the contractor, which can be costly, and also just increased project duration. So how do we mitigate those two costly impacts? Another thing too that we maybe don't always think about is the time from the last inspection to when we actually get boots on the ground to start chipping sometimes can be quite long. Contract processes take a while. It can take a while to save up money to do that work. How has that deterioration grown over those years is important to understand. This session is for decks, but I want to, very highlight, it's not just for decks. These things that I'm going to talk about, we can use on substructure, any reinforced concrete or any structure out there on, the bridge girders, the bridge piers, the abutments, the decks. So let's just not, close our minds to just thinking about decks too. Let's think about the other elements that we're having to service on these structures. What is really happening in the concrete? And today, I'm a concrete guy, so I'll kind of focus on concrete, but we go out and we do a sounding inspection, right? And we come up with an image that looks like this. Pretty common at an expansion joint at the bearing seat. We see, okay, we got some delaminations there. That was found by sounding. So obviously it's going to be a large near surface delamination that we found here. That the only thing that's going on here. What about the extent of delamination beyond what we can identify with sounding? We all know that delaminations start small. They start at small cracks, incipient deterioration that grow to these large delaminations. Most likely that delamination extends much further. So when we start chipping, we'll probably have to chip that much area instead of just the chalked off area. Well, also, what causes that deterioration? Well, corrosion is active, right? Corrosion is expanding, causing cracking and delamination. So maybe the corrosion is active beyond there. So we don't just have where we found with the sounding, that small area. We could potentially have other conditions occurring, and that deterioration is much larger. So how can we better really quantify what is happening in that structure? We want to know where these incipient deterioration mechanisms are so that we can identify quantity. My next slide, Shane did a nice job of introing this. Is actually pretty similar. We probably got it from similar sources. We've worked on some of the same things. Mine's a little bit different, but effectively similar. Concrete deterioration is exponential in growth, right? When we start to deteriorate, it starts to go very quickly. Here we kind of have just a general curve. We start with some initiation, and we'll kind of focus here on chloride exposure, but there's lots of different forms of concrete deterioration. So we start with chloride moisture ingress. Moisture and chloride start getting into the concrete. Then they start rebar corrosion. So corrosion starts to form on that bar. Corrosion is expansive, so we start growing an expansive product inside concrete. And as everyone's familiar, growing expansive products in concrete is very poor in tension. So we start to then get cracking, grow to delaminations, and then eventual spalling. And historically, we've used, chain drag and visual inspection as tools to identify conditions of structures, which are extremely important tools, and we need to be using those. We also want to identify some of these other deterioration mechanisms earlier in the process. And not only that, any structure that has spalling also has smaller delaminations and corrosion occurring simultaneously on the structure. So all these conditions are occurring simultaneously. So if we only use one tool to evaluate the condition of a structure, then maybe we're not really fully understanding the true condition. And that's why we're having trouble understanding the true repair quantities. So if we can use some other methods in combination, we can better understand truly what the condition is, and then maybe better understand our repair quantities. Obviously, visual inspection is still important, and I'm an NDT guy as well, like Shane, but we still need to be doing visual inspection. We need to be looking for these rust staining, cracking, spalls, where water infiltration is occurring, efflorescence. These are signs of issues. We need to be, visual inspection isn't something that's going to go away, and we need to be doing it better all the time. Sounding, another thing, a guy with a PhD you wouldn't think would be really into sounding, but sounding is a really effective tool for one kind of weird reason. When we talk about non-destructive testing and data, we look at, true negatives, true positives, false negatives, false positives. Sounding actually is kind of one of those weird where false positives are actually extremely rare. If you hear it debonded, desounded, you've got a delamination there. I've never come across a situation where you sound it and it sounds hollow and it's not debonded in some form. So it's actually quite an effective tool, but you have to understand its limitations. And with anything, understanding its limitations are key in using it effectively. You find those large near-surface delaminations, but you're not finding those incipient delaminations. So the false negatives, if it sounds solid, well, is it necessarily solid? Could it be smaller cracking that we just can't hear with the human ear? So I'm going to get kind of more into the fancier corrosion non-destructive methods, and I'm going to start with corrosion potential measurements, and I'm going to kind of call out a question earlier a little bit. By all means, I'm a corrosion engineer, and a comment got mentioned that, some accuracy on corrosion potential. I think, like with anything, it's about the person who's using it and how it's being done. Corrosion potential measurements are very accurate and can be very effective at finding corrosion activity in reinforced concrete. But it's important to know how to use that tool and use it effectively. So corrosion potential measurements, most people may be familiar with ASTM C876. This is half cell potential. So what you're doing in this method is you have a reference electrode and you're measuring the potential difference between that reference electrode and the steel rebar in the concrete. And the potential difference will tell you the probability of active corrosion. And that's important. It's the probability of active corrosion. So we've got a structure here where some delaminations occurring. Obviously, we found that with sounding. If we're just going to go out there and repair those delams, well, we could be missing a lot, right? If the area beyond that is actively corroding and we only repair these hashed out areas, we'll have to come back in a couple years and do more repairs, right? So if we can mitigate that deterioration in this whole area now, then we can have a longer, better repair procedure. Also, if we don't get to this delams for 2 years while we're saving up money, well, then when we come back, this whole area may be deteriorated. This is a good predictor at where the deterioration is going. My first example with corrosion potential, this is a bridge deck in Virginia that I did. Just some background, this bridge deck is actually very far along in the deterioration mechanism, so this actually bridge deck was replaced just because it was so deteriorated. But here we're doing corrosion potential measurements on a grid on the deck, and you can see that the kind of the hotter areas are areas that are indicating active, high probability of active corrosion. The green areas that are passive. And so this, there's quite a lot of area on this structure. And if we look at actually overlaying the sounding, so here's where we've gone and done a sounding investigation. So we know where the physical damage is today. And then we go do a half cell survey and we want to know, well, where is that corrosion active beyond these current delaminations and where is those delaminations going to be growing in the future? And you can see, obviously, we have some delaminations in this area, but we have a lot of high probability of active corrosion as well. So most likely those delaminations will be growing significantly in the near few years. Does it make sense to address it now or wait? And so this can be very helpful in understanding. And if we know we're going to take 2-3 years before we get to actually doing the repair work, then we know that our quantities will be growing beyond what we see today. And corrosion potentials can be used on substructure elements as well. So this is a bridge that I was looking at. And so we were actually looking more at the substructure elements because the roadway below was splashing moisture and chlorides onto the substructure elements. And this actual slide kind of gets me into, one of the things I think people kind of get hung up on corrosion potential measurements a lot is in ASTM 876, they have kind of a scale. And they give you some guidelines with -350. Anything more negative indicates high probability of active corrosion. But that scale is very specific for certain applications. And if you're applying that scale in every situation, you will have inaccuracies because you're not using it appropriately. I think it's important to show that this is corrosion potential of those columns and footing of that structure. And one thing to kind of notice, and it may be counterintuitive when you first look at it, one, this is not just the raw data. This has actually been processed and refined. And when we collected this data, the footing is very passive. And most people would think, well, why would the footing be very passive if the moisture and the chloride exposure is coming from the roadway below? And the columns and the lower portion of the columns are very active. And you can see there's some hatch marks. It's probably a little hard to see on the screen here, but there's some hatch marks where the delaminations are. And there's no delaminations on the footing, but only on the columns. Well, I'll get to it here in a few, but it really comes down to cover depth. The footings have very good cover depth, So the chlorides and moisture haven't really gotten to the reinforcing on the footer yet, but the columns had much less cover depth. So the chlorides and moisture, while not directly were splashing up onto those columns, had a much shorter path to the steel. So we're getting actually corrosion of the columns first and not the footing. But if you actually just, and I wish I had it for this discussion, but I didn't know we'd kind of get into a half cell discussion here today. The unprocessed half cell data actually showed that the most negative potentials were the footing. But when you processed and really looked at the data, it was just because of the moisture content, which as we know in the corrosion industry, moisture content will drive those potentials more negative. But you have to look more into the data to understand. While even though the moisture content was higher, the chlorides haven't gotten to the steel, and so passivity was still intact in the footing. That's just a little kind of thing to be cautious of. If you want to talk to me about corrosion potentials, I'll talk your ear off for days, but obviously we can talk about it after the presentation. But this is kind of an interesting example of where you have to be careful in understanding that these potential values that we get in ASTM are very specific to certain applications, and understanding how to process that information to get reliable information is critical. And so here on these structures, on these columns, we can see, yes, we have some delaminations in the columns, and they're very active, and so we need to do something to the lower portion of these columns to prevent further deterioration. I'll talk some about ground penetrating radar, and Shane did a great job of kind of leading that background information on GPR. It's an electromagnetic evaluation of reinforced concrete, and it's very useful in identifying deterioration. Big three things that we use it a lot for: reinforcement layout. If we don't know where our rebar pattern is, we can use GPR to identify that. Cover depth is extremely important in the service life of structures, so we can use GPR to really get some good statistics on that. But we can also use it for this qualitative condition assessment of reinforced concrete. When chlorides, moisture, cracking, corrosion, all these things start occurring in concrete, it can cause scattering and attenuation of the GPR signal. And so by looking at where that scattering and attenuation is occurring, we can identify where potential areas of problems are. And so here we have kind of a GPR signal. The bright white hyperbolas are the rebar, and you can see they're faded, attenuated in this area. So here's an area of potential concern. Do I know exactly what the deterioration mechanism is there? No, not exactly, but I know it's an area that I want to look at further. So it drives us to look at something more in depth in that location. Why is cover depth so important in our condition assessment and understanding repair quantities? I'm not going to throw a lot of equations out, just this one slide, but we don't want to get everyone lost on looking at random equations. But this equation is the diffusion equation for chlorides in concrete. And what it's saying is at some time t, at some depth x, the concentration of chloride in concrete. So if we have, x is the depth, t is the time, d is the rate at which chlorides are diffusing in the concrete. If we rearrange all of this and we want to say, well, how long, what time t, will our chloride concentration at the depth of the steel reach the threshold value? We see that the depth is squared. So if we have good quality cover depth, that has an exponential impact on the service life of our structure. Cover depth is the single most important thing, besides maybe quality of concrete, in the service life of structures, especially decks. So if we have good quality cover, we can extend the service life exponentially. So cover is extremely important in identifying where areas of deterioration will occur and where we need to focus our efforts. Looking at bridges, we can look at, say, cast in place reinforced concrete. Where are areas of potential low cover so that we know if we're going to have to address these as rehabilitation in the near future. So looking at some columns, we do some GPR scans, and then we create some nice plots. And we can see that this structure was actually having some issues of spalling, early age spalling in the structure. And the reason being was because some specific areas had very low cover because they didn't tie the reinforcement very well, and it was really close to the surface. It was getting carbonated concrete, causing corrosion and eventual spalling. Did they have to do complete total repair of the substructure? Absolutely not. They just really needed to repair these localized areas. So by doing the GPR survey, we can identify where their corrosion activity is going to be and how much area needs to be repaired in the next few years to mitigate this low cover corrosion issue because of carbonation. And this helps better refine their quantities and know the service life of this. So we don't have to do work to most of the column area. We just have to focus on the low cover areas. And so we can better refine that information. With the amplitude assessment, this is actually a bridge in Florida. And in Florida, we don't have a lot of deck issues because we don't put de-icing chemicals on anything. This was a unique issue, and if you look, this is the bridge down in Naples, and you see there's a marina right here. And as we know, people go out fishing, they pull their boats out of the water, they're dripping with salt water. Every state has signs to wash your boat off, plants, we don't want cross-contamination. How many boaters actually do that? Unfortunately, very few. And so what they end up doing is they pull their boat out of a salt water and then they drive it over the bridge deck. And what happens is they're dripping salt water on the bridge deck. So this is the west. So north is up on this image. So they're headed eastbound on this structure right after they pull their boats out. And as you can see, if we do GPR scan of the deck, where's all the attenuation occurring on this deck? Eastbound, very early in the spans. So this is only the beginning 400 or 500 feet of the bridge. So I just for sake of image, I cut it. You look at the rest of the bridge, only the first few spans on the eastbound side were having any issues. And it was all because of salt water dripping off the boats. By the time they got kind of halfway over the bridge, they've lost most of the salt water off their boat, or at least most of the dripping. The rest of the bridge deck was okay. So here we can use GPR attenuation to really quantify where's the attenuation occurring, where's the deterioration going to occur. And we can focus the DOT's money on these first few spans in the eastbound section for them. And so they didn't need to do widespread work. They really just needed to focus on this area where the boats were dripping water onto the deck. And hopefully get the boat owners, maybe buy a hose for them so that they wash their boats off. Another method that we use a lot to assess quantities of bridge deck deterioration or bridge deterioration is acoustic methods. A lot of people are probably familiar with impact echo, where we make an impact. It's effectively a very fancy chain drag. Chain drag is limited by the acoustic property of what we can hear with the human ear. So we can get fancier ears. We just use sensors. So we make an impact, and then we monitor with sensors the vibration of that stress signal in the slab. And we can effectively, based on the frequency of vibration, we can identify the thickness of this slab. And if there's a delam causing that frequency that stress wave to vibrate at a higher frequency, then we can identify that there's some delamination or incipient cracking that's occurring. What if we also have kind of cracking, vertical cracking? Impact echo is not as responsive to just simple cracks. It's more debonding, delamination, things of that name, more parallel activity. So if we use an array of sensors, not only are we monitoring the vibration of the stress wave in the vertical, but we can also look at the velocity of that wave between sensors. So we can look at velocity, and that's much greater effect due to cracking, vertical cracking. So if we have cracking between the sensors, that's going to affect that wave velocity. So by doing these acoustic methods, we can really understand cracking and delamination in concrete before it becomes visual or sounding that we can hear. Another nice thing with the wave velocity is that we can use shear wave velocity or wave velocity of a stress wave to calculate concrete compressive strength. So we can get an in situ compressive strength of concrete based on the wave velocity. And if there's cracking, that will obviously affect that wave velocity. And so by looking at in situ compressive strength, we can identify areas of low strength, which indicates cracking and other things like that. For decks, a lot of people, and Shane showed one, a lot of rolling impact echo kind of types. There's several different systems out there that work. So this is our particular one. It has a couple of sensors on some wheels. So it's got 3 leading sensors, and then it's got 1 trailing sensor. And the reason for our trailing sensor, we have it in kind of 2 dimensions, is that not only are we getting surface wave velocity that way, but we're actually getting wave velocity in the rear. So we're getting cracks that are longitudinal cracks, but also transverse cracks. So if you're measuring the wave velocity from sensor 1 to 2 or 3, if the crack is parallel with that wave, it's really not going to pick it up. The wave velocity is really affected by the transverse cracking. So by having a trailing sensor, we can get also transverse cracks and really understand a condition. So the rolling impact echo goes over the deck, and because it's more sensitive than, say, chain drag, we can really identify more of that incipient deterioration and find those delaminations before they've grown to the size that sounding can identify. Now with impact echo, unlike chain drag, there will be false positives and false negatives, and so you have to understand how to analyze that data. And doing chain drag in combination with impact echo, I think, is still very positive because okay, here's where the large delaminations are, where's those incipient delaminations beyond that, and really understanding those quantities. And so with bridge decks, it's very common to be doing rolling impact echo. But also we can do it on substructure elements as well. We can have a handheld version of the sensor and an impactor and do it to find an identify those quantities on the substructure elements. And this happens to be a tunnel abutment wall. And so I'm just going to show kind of a little bit of a piece of that area. So, when we go on a certain area of the structure, so this is 24 feet by 6 feet, and we just did a sounding survey. So we have a joint here, a vertical joint, and obviously around joints, we tend to get a lot of delamination. So sounding found some delamination around the joint, and then a little small area out here. Well, what if we then go and do impact echo? Where's the delaminations beyond that? Where's the incipient delaminations? And you can see that those areas grow quite a bit. There's strong agreement around the joint that that's all delaminated, but actually the area that was just here, that's grown a lot. So we know that delaminations actually form much larger. So when the contractor starts to chip into that, he's actually going to end up chipping probably most of this out. But also we have the stress wave velocity, in situ compressive strength, and that's really going to be identifying cracking, vertical cracking, horizontal cracking. So where's that come into play? So if we overlay that information, so then we start identifying, areas of weaker concrete. So this is maybe where it hasn't created a delamination quite yet, but it's starting to crack, micro cracking starting to occur, affecting the concrete. And you can see this is just a highlight scale. So effectively, green is like over 4,000 PSI concrete. Yellow and reds are less. And we can see that the concrete's really weak around these large delamination areas. And so we have identified that, okay, well, if we start chipping these areas out, it's going to grow quite significantly because we've got low, weak concrete. So in reality, our repair area is quite much larger than what we initially thought with just pure sounding. So we can better quantify the areas based on that assessment. And so now we know really what they have to go out and repair and put that into the bid repairs. If there's any questions, I'll be happy to answer.
Not so much a question, just more of a footnote to your false positives on sounding comment. We found in Oregon preserving a lot of 1930s structures that we were removing a lot more concrete than we intended due to not so much false positives, but construction defects that have been there for 80 years was not really harming the structure. And this consisted of very large aggregate. I'm talking 3, 4, 5, in some cases 6-inch rock that made it into these members, and poor consolidation at cold joints. Sometimes we wanted to repair it where this poor consolidation was offering poor corrosion protection around bars. We want to go in and get some good material back around those bars. But in a lot of cases, it had survived 80 years of service, was not causing overstress of the members, and we want to leave well enough alone. So we instituted, if there was disagreement in the sounding, this often sounded a little bit different than your run-of-the-mill DLAMs. So if there's disagreement, we would use a rebar locator, GPR. If there's no bar there, we just move on. If there was bar there, little exploration, saw cut area, dig down. If there's no corrosion, patch it back, move on. If there was corrosion, we would repair it as normal. So if anyone does preservation of those structures, thought I'd make mention that it's not really a false positive because it is a defect. I don't think the designers intended for that to happen, but it's not really it's a deficiency of the structure if it's in service and performing well over that period of time.
Rock is very impervious to chlorides, which is nice. So your rock is probably the boundary mechanism.
You guys obviously promote the sacrificial anodes.
I'm Vector Corrosion Services. I'm an engineering firm.
But do you get involved? So it's different. So
well, I mean, I do promote cathodic protection and corrosion mitigation, but
okay.
Yeah.
So this would still would be a question in line. So let's say you sound an area that's delaminated, but you suggest that there's other potential areas for further corrosion. Are the sacrificial anodes effective enough that you could just cut out the areas that are sounding as delaminated, put the sacrificial anodes in there, and then the corrosion potential outside of that area now would be, I guess, neutralized from that? So you would not have to actually cut out, is the larger areas greater than what sounded? You wouldn't
Right.
have to use those ultra-sensitive methods?
So that's a very good question that kind of leads from my presentation is right. So, okay, so there is more damage than we see, right? You have delamination and then maybe incipient action, maybe it's just corrosion activity. Do we have to chip it out to repair it? No, not necessarily. And you're alluding to, if you're not familiar, there are galvanic anodes, and there are galvanic anodes that can go in repair areas, and there are actually drill-in anodes that can go into sound areas to stop corrosion. So you drill and then grout them in. So there are those options to mitigate maybe some of these incipient problems before you have to chip them out. So chipping isn't the end-all be-all solution, and that's a good point to bring up, is there are ways to, if you detect the deterioration earlier, then what are the methods to stop that deterioration earlier? And galvanic anodes are one of those tools in the tool bag, and there are anodes for inside the patches and also in sound concrete. Just to note that the anodes inside the patch, they have a limited throw outside the patch, so you have to just be careful about, okay, knowing that I'm only really protecting, 2 feet from the patch. So if I have active corrosion 4 feet away, maybe I need to drill something in that location. So just understanding the tool and how to use it would be key. But yes, those are options in that situation. That's good.
The half cell potential. Could you go into a little more detail of how you do that survey? The ASTM showed, attaching to the rebar, therefore you have to excavate and do. And so I'm wondering if that's, because I think some of the corrosion half cells that I've seen didn't do that. They were just from one point to the next point, so you weren't doing destructive testing, if you will. And then the other piece you talked about was the post-processing. What could you go a little more detail of what actually you're doing in the post-processing? Because I imagine you're figuring out where there's moisture. Well, what tools are you using to figure out where there's moisture and not moisture? So maybe a little more detail on those two. So
the first question about contact to the rebar, if you're working with somebody who's not contacting to the rebar, I would be, they're not doing ASTM 876. You have to make a direct connection, electrical connection to the rebar, and you also have to verify you have electrical continuity of that rebar. So you have to make multiple connections. So usually what we do is we just make a small 3/8 drill hole to a bar, do it in a couple of locations on a structure, measure electrical continuity. Okay, we're good. So we know we have electrical continuity, and then we typically would just use one anchor point to kind of do the survey. Structures, most cast-in-place structures will have electrical continuity, so a lot of people forgo that step, but however, pre-stressed elements, pre-cast elements, and pre-stressed elements tend to be more electrically discontinuous because at cast-in yards, they don't need to do a lot of tying. Also, post-tension structures are different and stuff, so that's an important thing to do. Some emerging technology out there trying to get away from making contact to the rebar, but none of that is really out heavily on the market just yet. Be a little suspect on anyone who isn't making a contact to the rebar. Obviously, epoxy-coated rebar also provides continuity issues. There are ways to get around that as well. With regards to the analysis, a lot of that, I have to be, I don't want to give all my secrets away, right? That's why people hire me. But what you're really, one is I'm not really measuring directly the moisture content. I'm really looking at how the potentials are changing. With my slide there, it's not about the absolute value all the time. The absolute value is one tool, but you're also looking at, okay, are we seeing a lot of changes on the potentials? And that can give you an indication that active corrosion is there, because we're looking at corrosion's an electrochemical reaction. So any electrochemical action takes potential difference. And that's really what you're measuring here is potential difference. And so by understanding that, you can account for some of those moisture content issues.
One of the comment that I want to make is that with regard to the half cell potential measurement, particularly for epoxy-coated decks, you have to be very careful. The standard doesn't allow you to use that methodology that is specifically for black bar. So if you're going to use epoxy-coated rebar evaluation of the deck, you really need to do a lot of different things to figure out what the condition of the deck is. Half cell would not be one of them.
Knowing that ASTM 876 is for uncoated decks is kind of critical, and just how. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.